Right, so today we're going to look at another kind of excitation inside solid systems, and that is we're going to consider electrons. So far we've done two major things in this course. First of all, we've looked at the structure of matter, precisely the crystalline structure of matter, see how that structure is described, how that structure is then determined using diffraction methods. In the second part of this course, we've relaxed this notion that all the atoms are at fixed locations. Rather, we've seen that they can oscillate about equilibrium points, and that led to the creation of new quasi-particles called phonons, which are bosons. They have their own distribution, and we can look at the energy content that exists or resides within these quasi-particles, and from that we could determine the heat capacity and look at other properties. And if you have some novel system like in 2 dimensions with a particular kind of interaction between atoms, new dispersion relationships for those phonons appeared. So there were 2 or 3 lectures that were given in a sense asynchronously online. Those are not to be missed, even though we haven't interacted face to face, but those are a part of the discussion that we've had for this course. So do not evade yourselves from looking at that material. Okay? So today we're going to, I had wanted to do more things with phonons, but if time allows in this course, we'll do this at the end of the course. But I would like to immediately shift gears and talk about electrons, because the electrons are the second most important excitation that would exist inside a solid system, and they would lead to electrical properties of all kinds, and optical properties, and magnetic properties, and thermal properties, right? So let's look at electrons, and the first thing that we would like to look at is if these electrons are totally free, which means that electrons are not interacting with one another and they're not interacting with the ions in the system. So this of course is an assumption, but it holds water for a large variety of solids, especially metals, and particularly metals that are on the left of the periodic table, the alkaline metals. So let's look at electrons. This is lecture number 17. And we're going to look at free electrons. So inside a solid, say a metal, let's consider sodium, atomic number 11. And if you look at the electronic configuration of the sodium atom, it's 1s2, 2s2, 2p6, and 3s1. So this electron in the valence shell, so far away from the nucleus that it can go, the atom can be ionized, and this sea of electrons now exists and is roaming around freely in this framework of positively charged ions. Okay? So this sea of electrons is like a continuous medium that is homogeneously distributed inside this metal. So now these positively charged ions do have their own potential, and if you look at atomic potentials, and if you just draw a particular section inside this solid, let's call this axis X, we do know that these ionic cores will have their own potentials. So if this axis is my potential energy axis, then these ionic cones will have this central potential or something similar, where this spacing is equal to the lattice spacing A, and so on. So there will be these functions, equally spaced periodic functions, that correspond to the potentials caused by the positive ions. But all of this is homogeneously distributed, and the electrons are also homogeneously distributed. So for a first approximation, we can ignore, we can just imagine that these free electrons, the sea of electrons, or the conduction electrons as they're sometimes called, they are swarming around in a positive, uniform, homogeneous background of positive ions. Okay, and since the electrons are also homogeneously distributed, what the interaction between the electron and the mean positive field, the mean field will just be a baseline, a constant. Okay, so under this assumption, we could say that the electrons are just seeing a mean positive potential. This model, by the way, is called the Jellium model, or the mean field model. Okay, so in the Jellium model, we would assume that the electrons are just seeing a positive bias due to all the ions, and this bias is homogeneous. It does not depend upon where the electron is inside the system, and the electron itself is also delocalized. Okay, so in this, and the assumption on top of this is that the electrons are not interacting with one another. They're non-interacting electrons. Okay, so this is the first assumption. Such electrons can be called free electrons. And each electron will then just be a free particle. And the Hamiltonian for the electrons, for any electron, the nth electron will just be the momentum squared of the electron, right? For the nth electron, this will be the Hamiltonian, and this will be the time independent Schrodinger equation. Yes.
So you said it is seeing a positive potential, mean positive.
So but that positive potential is just some background, and you can take this background to be 0. Okay. So now this is the Hamiltonian for free electrons, and the total Hamiltonian for the system could just be, since the electrons are not interacting with one another, would just be the sum of all of these Hamiltonians. Now we know that this is the time independent Schrodinger equation. It represents a free particle. So the wave function, the quantum state for any electron, psi L, inside the system, I can also drop the L subscript, will simply be the wave function for, what I'm doing here is plotting the wave function, right? I am writing on the wave function is Eik dot r, right? That's a free particle. And we would like to normalize this with, say, some constant. Let's call it the volume of the solid, the total volume of the solid. So this is the wave function for free electrons inside our alkali metal under the Jellium approximation. Yes?
So how are we summing up an operator? Is that a tensor product or a direct product?
So okay, it's a tensor product. Alright, so now we know the wave function of this free particle. So this, if you would like to draw this wave function, the real part of this wave function will just be some sine wave, right? So this is how this particle is acting like inside this solid. But of course the solid has finite dimensions. So this value of k cannot be arbitrary, it is discretized. The confinement is causing quantization of the k values. And we can apply the periodic boundary conditions, the Born-Kármán boundary conditions, the Born-Kármán boundary conditions, and discretize the values of k's as we've done for the phonons. Okay, so if we just have a one-dimensional system in which the lattice spacing is, say, a, then we do know that the wave function EIKR must be periodic. So if R is replaced by R plus L, where L is the length of the solid, so what you can imagine is that you have a chain of atoms in 1D and you make a ring out of it, so that the start and the end, they coincide. So the wave function must be periodic at the ends. Okay, so because there is really no distinction between the two ends of the solid, so the wave function must match at the two ends. This is called the periodic Born-Kármán boundary condition. So EIK dot R must be the same as EIK R plus L. In 1D, this is simply EIKR equals EIKR EIKL. And since we're talking about just along the x-axis, so this is kx. So this must be equal to 1, which really means that kxl must be some fraction of 2 pi, which is another way of saying that kx is now quantized 2 pi over L. Okay, so if L is the length of this solid, kx, the distance between two consecutive k points in k space, is 2 pi over L. Okay, so if I were to draw the same wave function in k space, this is my kx space, any two consecutive points will be separated by 2 pi over L. Correct? So what we could now say is we can extend this idea to 3 dimensions. In 3 dimensions, what we could do is we would like to plot the wave functions, the allowed wave functions in the reciprocal space. So the wave functions in the reciprocal space are defined in terms of the allowed k values. So k is quantized along x, along y, and along z. So if I were to draw the reciprocal space for these free electrons under the periodic boundary conditions which arise due to the finite size of the sample, I'll get a grid of points. So I will get points along this axis, along this axis, along this net, along this net, the kz, ky net, and I will create a large number of interconnected points. So this entire volume will now be split up into cubes. Okay, and since it's a large solid, we can ignore this shape and geometry of this solid. It's a large solid, we can assume it's a cube. Okay, so if this k space, the reciprocal space, which is now the space in which these periodic, these wave functions exist, has now been split up into these fine cubes. Now let me zoom in onto one cube. So this is a cube, and these are the allowed discretized k points, and the wave functions have any one of these k's or superpositions of waves with these k's. Correct? Now this dimension, each of these dimensions is 2 pi over L. Lx, Ly and Lz are just the same because of the large size of the sample, and we are far away from the surfaces, so no surface effects are taking place here. So this is not nanotechnology, this is a bulk solid, a macroscopic solid. So this volume is really 2 pi over L cube. So the size of each of these cubes, let's call it delta K. This is, let's call it delta, the volume in the K space is 2 pi over L cube. So the wave functions for the electrons, the free electrons inside this solid, are now represented by this fine grained structure, and each k point represents a particular wave function. Very similar to what we've seen for phonons. Now the next step in this argument is to find out the energy of these electrons. So let's move on to energy. So first of all, we've seen that for free electrons in the Jellium model, the electrons exist as plane waves. Because of quantization, their k values are quantized, and in the k space we can denote each wave by a point in k space, the reciprocal space. Now let's talk about energies. What energies do these electrons have? So an electron has a certain wave function. That wave function is an eigenstate of the Hamiltonian, which is just the kinetic energy operator. So the eigenvalue of that Hamiltonian will just be the energy of the electron when it exists inside at that k point. Remember, for phonons we connected omega with k. That was a dispersion relationship. Omega is energy. So energy depends upon k. Exactly the same ideas apply to electrons. And it's even simpler for electrons, because for phonons you had to come up with these nonlinear relationships between omega and k, unless you just talk about the speed of sound. So here it's nonlinear as well, but it's a simpler relationship. So by just looking at the Hamiltonian, you can tell what the energies are. So what are the energies for the electrons with different k values? Right. So the energy for the electron, the certain k value, is simply h bar square k square, which is the square of the eigenvalue of the momentum operator over 2m, the mass of the electron, the physical mass of the electron. Okay. So now consider a point in the k space, this point. This has a certain value of kx, certain value of ky, and a certain value of kz. So an electron with this wave number will have an energy h bar square over 2m kx square plus ky square plus kz square. And this is simply one of the eigenvalues for the Hamiltonian for the free particle. Okay. So now this k manifold can be translated into an energy manifold. Agreed? And different Ks can still lead to the same energy. So there's some degeneracy associated with different Ks can lead to the same energy. There's degeneracy. It's just like an infinite well. Now this is a three-dimensional infinite well. Okay? So the electron inside the solid is in fact inside a three-dimensional infinite well. That's what the electron really is, as far as the free electron is concerned. So we're doing nothing but the three-dimensional infinite well here. So by looking at this relationship kx, ky, kz and noting that each of these k values is quantized, the energy for the electron can also be written as h bar square, sorry, this is h bar square over 2m. Now each of these kx's is a square, so I take 4 pi square L squared nx squared plus ny squared plus nz squared, where each of these n, x, y is an integer, right? And all three of them are not equal to 0 at the same time. So this energy which is now quantized for a given k value is described by these three quantum numbers nx, ny and nz. So this is the energy of free electrons inside the solid. Got it? So all of this is simply k square, which is k dot product with itself. Okay, so now we have the energy for the electrons, for the free electrons inside the solid. The problem is totally analogous to the 3D infinite well. Now what we would like to do is, suppose we have this solid, there's a large number of electrons inside the solid. Look at the top, large number of electrons inside the solid. There's some size of this solid, and we would like to know how many modes exist, which the number of modes is just the number of k points. The number of k points is going to be the number of modes. Each k point is a mode, is called a mode. It has a particular energy and a particular value of the trio kx, ky, kz, right? On top of this, we're talking about electrons. So electrons also have spin. Phonons do not have spin because they are bosons, their spin is 0, but electrons do have spin. So on top of this k-space picture, we would also like to emphasize that electrons are fermions, they have spin, and they are spin half particles, the fermions, and each k point can harbor or hold 2 electrons, but with opposite spins, because electrons are fermions, so they must obey the Pauli exclusion principle. Okay, so what we would now like to do is, do we know how many electrons exist inside the system? What would we need to know if we were to tell how many electrons exist inside the solid? What parameters would we need to know? We need to know the density of this solid. We need to know the volume of this solid. We need to know the atomic mass of this solid. This will give us, we need to know the number of electrons that come from each atom, the valency. That will tell us the number of electrons that exist inside the solid. Okay? Now, yes, please.
जब हम कह रहे हैं कि Pauli exclusion principle apply हो रहा है, so isn't it sort of saying that they are sort of interacting the electron?
There is no Coulombic interaction. Okay? So it's it's the nature of electrons, and it's a different perspective that's a kind of interaction. But when we say interaction in solid state theory, it's really about Coulombic interactions or other kinds of interactions, or there has to be a potential energy associated with it. So if you know all of these parameters, you can tell how many electrons exist inside the system. So those electrons, since they are free particles, they have to populate that K space. And they must start populating that K space, and each point has a particular energy. And we know that each point cannot harbor more than 2 electrons. So those electrons have to be paired. So if you would like to have n electrons, and those n electrons have to be populated onto these K points, you can't just put all electrons on a particular K point, on the K point which has the lowest energy. So they have to be distributed, and you have to distribute the electrons bottom up. So first of all, 2 electrons will go to the lowest points with the lowest energy. There could be some degeneracy as well, and then you successively build up this K space. Okay, keeping in view the Pauli exclusion principle. So if I were to draw the K space at some, suppose first of all I'm at 0 kelvins, absolute 0. So at this temperature, everything would like to go to the lowest energy possible, while respecting that these electrons are fermions. So if on this scale, since n could be very large, even if I have a 1 millimeter cube sized object, the number of electrons will be extremely large, right? More than probably Avogadro number of electrons. So on this scale, there would be many K points that will be populated. So what you could imagine is that there is some region, some volume inside the K space which is filled at 0 kelvins. And there's a boundary between the filled and the unfilled space in K, in the reciprocal space. So what shape would that volume be? It's a sphere. Now this shape separates the filled and the unfilled space in K space. So this shape is called the Fermi sphere, and this surface is called the Fermi surface. So this is the Fermi surface. अभी ये kx की बात हो रही है, ये पॉजिटिव भी हो सकते हैं, नेगेटिव भी हो सकते हैं, ठीक है? अभी हम K स्पेस में. So the Fermi surface separates the filled and the unfilled part at 0 kelvins. Okay. Now, if this radius is Kf, the volume of the Fermi sphere is given by 4/3 pi Kf cube, and the number of electrons that can exist up till this Fermi sphere, it will be given by this volume divided by the total number of K cubes that are available. So this will be Vf divided by this Vk that we've written over here, delta Vk. Correct? Because we have this large volume, and this large volume is composed of these tiny cubes, millions of them. And since each of these K cubes is associated with 2 electrons because of spin, you can put a factor of 2 here. So this will be the total number of electrons inside the Fermi sphere. So if n is known, because n comes out from these parameters, delta Vk is known from the size of this object, we can see what the size of the Fermi sphere should be. You can find out what the Fermi velocity is going to be. Okay, so if this is 2, this is 4/3 pi Kf cube, This is 2 pi cube into the volume of the solid. This becomes 1 over 3 pi square kf cube. This is n over v, the total number of atoms in a volume capital V. We're talking about electrons. This is the charge density, or the number of electrons per unit volume, small n. So kf, the Fermi velocity, is really 3 pi square n, small n, raised to power 1 by 3. So if you were to know the charge density, which comes from the valency, the atomic number, and the density, we can tell what should be the Fermi wave vector. That will be the Fermi wave vector. That will be the wave vector associated with the maximum momentum that's available for the electron inside the atom. And associated with this Fermi vector, there is going to be a Fermi energy, EF, which will be h bar square kf square over 2m. Okay? And every energy can be written as Boltzmann constant into a temperature, right? Every energy is kT. kT has the same dimensions as energy. So associated with some energy. Now this energy is not coming from heating, it's not coming from pressure being applied onto the solid. This pressure in a sense is the degeneracy pressure for the electrons inside the solid. Degeneracy pressure, which means that the pressure that is coming from the Pauli exclusion principle, right? The Pauli exclusion principle forbids more than 2 electrons on each k point, so the energy keeps on building, right? Similar paradigms exist on neutron stars and other massive objects in which neutrons are compressed, because neutrons are also fermions. So this solid itself sees this very large Fermi energy, which could be of the order of 5-6 electron volts, depending upon which metal we're talking about. So for different metals, you can find out n. It's a classical calculation. You can find out the density of electrons. Sodium, potassium, francium, rubidium, calcium. You can find out what n is. You know the densities of these objects and you know their valencies. So you can find out what kf should be, what ef should be, the Fermi energy should be. Turns out to be of the order of few electron volts. So this EF is sometimes written as KB TF, where TF is called the Fermi temperature. So the Fermi temperature can be very large for electrons. If you have a solid at room temperature, the thermal energy for an electron, so if I'm talking about solid at room temperature, you just put a solid at room temperature, the motion of the energy associated with the thermal motion of the electrons, which is called Johnson noise. The Johnson motion could be as Kb, the T, the ambient temperature. So this is 300 kelvins, joule per Kelvin to 300 Kelvin. You divide this by to get an answer in electron volts. This turns out to be around 25 milli electron volts. 25 milli electron volts. But the TF, this is of the order of say 5 electron volts perhaps. So TF over T is much larger than 1. In this case, this is about 5,000 over 25, 200 times larger. So the Fermi temperature for the electrons inside this solid, which is not due to the thermal motion, it's due to the Pauli exclusion principle, gives rise to a very large effective temperature for the electrons inside the solid. All right? So this is an important point to consider. Yes, please.
Calculating the number of electrons, the electron density, did we assume that there are equal number of spin up and spin down electrons?
Yes.
And is that like a reasonable assumption?
That's a very reasonable assumption if there are no magnetic fields and we have a paramagnetic, non-magnetic material. ठीक है? Because there is no preference for electrons to align in a particular direction. So as far as the spin is concerned, it's a totally mixed state. All right, any questions about this point? Now so what we've done, first of all, we saw that free electrons exist. That's a zeroth order assumption for electrons inside solids. Then those electrons are described by these plane waves. However, due to the finite size of the object, all k values are not allowed. K is discretized. So the k structure becomes striated, which means you, instead of a continuum, you get these points, discrete points. Each point corresponds to a certain energy. And then you would like to fill up those k points up to a certain sphere called the Fermi sphere. And all the action really inside solids that is accounted for by electrons, like conductivity, magnetism, magnetization, happens at the Fermi sphere. Suppose you have, just to give you an example, suppose you have this Fermi sphere, nice sphere, and you put an electric field on the solid. So what the electric field does is it raises the energy or lowers the energy of the electron. It raises the energy for electrons, right? Because E times small e times capital E, where E is the electric field, the energy changes because you've applied a potential difference. So this Fermi sphere might change its location. The number of electrons is still going to be the same. Some electrons might increase their energy, but an electron that is deep inside the Fermi sphere has nowhere to go because all other neighboring k points are already occupied. Right? So only the electrons at the Fermi sphere in the immediate vicinity of the Fermi sphere do they see vacant k points. Only those electrons can be excited. If you provide thermal energy to the system, the internal energy changes. The internal energy changes means that some electrons may raise their energies, but only those electrons that are close to the Fermi sphere are able to raise their energies. So all the drama in electronic solids happens at the Fermi sphere. Therefore, the shape of this Fermi sphere, the size of this Fermi sphere is really important. Nothing is happening inside, or magnetism is happening at the Fermi sphere. Okay, so now we would also like to figure out this analogous concept that we studied for phonons, and that's the density of states. Remember that for phonons, we had a density of states, g omega. The number of states that are available at a particular value of omega. And this g omega depended upon, it was inversely proportional to the group velocity, which was the slope of the dispersion relationship, d omega over dk. Okay, so you find the dispersion relationship, from there you will get the density of states. You will not find states uniformly at the different values of omega. Correct? Likewise, for electrons, we can also define a density of states. Let me give you an example. Let's denote that density of states for electrons. Let's call it D at E. That's conventional. You can also call it G at E. I'm just trying to be specific here. I'm talking about electrons, so I call it capital D. Some authors call it G. I also sometimes use G, but let's call it DE. So DE is the density of states for these electronic modes. Let's find out the density of states in 3D. Now we do know that if I have this K space, and we just draw a shell, and this is Kx, Ky, Kz. So this is a three-dimensional cell, a three-dimensional sphere, and this is a tiny, tiny thin veneer inside this shell of thickness dk. This shell has thickness dk. So how many electrons or how many modes will exist inside this dk? Let's call it dn. Exactly the same kind of calculation that we did for phonons. So dn will be the volume of this shell, which is 4 pi k square divided by the number of k points that exist inside the cell, which is divided by the volume of each of those k points, which is delta Vk, and you multiply by 2 because you want to take into account spin as well. So this will give me 8 this will give me 8 pi k square over delta Vk is 2 pi cube, which is 4 pi cube over L cube, which is the total volume of the solid. So I will get 2 k square volume of the solid over pi square. This is my dn. 2 pi का क्यूब लिया ना ये वाला. So this is my delta Vk. ओहो 8 pi. Sorry ठीक है. Sorry ठीक है. Remember, this capital V is the total volume of the solid. So inside this thin veneer of a shell in the K space, dn electrons exist, right? So but this dn must equal capital DE, right? So this must equal, so what I could do is, by the way, there's a dk here as well. Don't forget the dk, 4 pi k square dk. So my dn is volume k square over pi square dk. This equals capital DE dE. So what I could now do is I know that the relationship between E and K, which is the dispersion relationship for electrons. Once again, I'm using the dispersion relationship for electrons as I've done for phonons. This is h bar square k square over 2m, which means that my dE equals h bar square k over m dk. So I take this dE, put it in here. I will get dE. My dE is now h bar square k over m dk. So this dk, I can let this go. My dE therefore turns out to be v k square pi square into m h bar square k, which is v k m h bar square pi square. Correct? So I would like to express this dE in terms of energy instead of k. So I take the dispersion relationship again. I do know that my k is, as we all know, for a free particle 2me square root over h bar. I take this k and insert it in here. I will get volume over m h bar square pi square 2me 1/2. This additional h bar will come here. So this is my density of states, dE. All of this I can lump everything else into a constant. By the way, generally you put density of states. So what are the units of density of states? So per unit energy. Generally you express the density of states as per unit energy per unit volume, which is really tantamount to taking this volume to the left hand side. So you do a specific density of states per unit volume. Okay. So all of this is some constant which depends upon fundamental constant, the mass of electrons, h bar and so on. But the thing to notice is that the density of states is proportional in 3D. We talk about a 3D solid, is proportional to the square root of energy. This is, I think, if you were to take one lesson from this condensed matter physics course, it's about the density of states. For electrons inside a solid, the density of states is proportional to the square root of the energy. For phonons, the density of states was totally different. For the Debye model, it was omega squared, 1 over omega squared. So the density of states depends upon the dimensionality, it depends upon which quasi-particles we're talking about. And those excitations are defined in fact by the density of states. So the density of states for electrons in 3D is equal to some constant, right? So this is the result for 3D. Okay, so this is for 3D. And I'll give a homework problem in which I'll ask you to do this for 2D. For 2D, the density of states turns out to be equal to some constant. It is independent of energy. So if you have a nano-sized film, a two-dimensional structure, a two-dimensional crystal, an atomic layer, the density of states does not depend upon the energy. For 1D, another homework problem perhaps, this density of states is proportional to some constant minus 1/2. What do you think would be the density of states for a zero-dimensional particle? Quantum dot. So if you confine an electron on a dot, just remains there, you get Dirac delta functions. The electron becomes, the energies become quantized. Only particular, just like an atom. An atom is a zero-dimensional structure. So what do the energy levels look like in hydrogen? They're just 1 over n square, but there are precise energy levels, right? They are minus 13.6 over n squared electron volts, but they're precise, so they're Dirac delta functions. So for zero-dimensional objects, which are called atoms, zero-dimensional objects are atoms or quantum dots, which are also artificial atoms. So you'll get some series of Dirac delta functions. Okay, so the dimensionality controls the density of states. If I have to plot all of this in 3D, this is my E, this is my DE. In 3D, the density of states has a square root function. This is 3D. In 2D, it's constant. In 1D, it might go down like this. Right? And as far as an atom is concerned, it could be a series of Dirac delta functions. So the density of states is really important. And the density of states is used for calculating macroscopic properties for this gas of electrons. Now remember, for phonons, which were excitations associated with a bosonic field, we called phonons a gas of phonons. The phonons were particles, and even though we're talking about crystalline oscillations, we just can't treat those particles as a gas of particles. Here we have a gas of electrons. Okay? Non-interacting gas of electrons. So now with this, equipped with this density of states formalism, and remember, so far we are only at 0 kelvins, we can find out properties associated with these electrons. But any questions? One kind of small departure I would like to make now is kind of relax this condition for 0 kelvins a little bit. Yes. No, we haven't. So one thing I would like to mention is that if I take, one nice thing at 0 Kelvin, one nice calculation is if I look at the Fermi energy EF, suppose I'm at 0 kelvins. I want to find out the Fermi energy. I give this question to you to kind of think about next 2-3 minutes. I know the density of states for 3D is proportional to the square root of energy. I'm at 0 kelvins. So what this graph tells, the green graph tells, is that as the energy changes, how many modes are available? How many energy states exist? Now that's a different question whether that energy state will be populated or not. But if at 0 kelvins, if all prior energy states have already been filled and an energy state is available at the next energy in line, the next electron will go there. Okay. So this is how these energy states are filled up. First of all, you fill up the lower energy states, and then you keep on building up all the electrons inside the system. And remember, it doesn't happen in a sequential fashion, it just is there. When I am explaining it in this fashion, that first the lower energy levels are filled, then the high energy, it doesn't happen sequentially. It's God or nature has made it such that you find that all the electrons up to the Fermi energy are filled, right? So it's not a sequential preparation of an atom that we're doing or of a solid that we are doing. Now at 0 kelvins, if I would like you to, you know what the density of states look like, can you find the Fermi energy? For that, Fermi energy, you need to know the number of electrons inside the system. Suppose the number of electrons is capital N. So if capital N is large, will the Fermi energy be higher? If you have more electrons, higher will be the Fermi energy. Correct? ठीक है ना? By the way, this density of states does not depend upon the chemical nature of the metal. सारों की बात कर, there's nothing, it's just related to the fundamental constants, right? Does not have anything to do with the density of states. Is not is the same for sodium and for potassium. Now the question is that if I have n electrons, can I find out the Fermi energy? Simple question. चलो वॉल्यूम भी पता है, 3 पाई स्क्वायर n, ठीक है, इससे पता चल जाएगा ना, 3 पाई स्क्वायर n, ठीक है, ऊपर इससे kf आ जाएगा, ठीक है. So what's the relationship between EF and N, capital N? You can also find out that relationship. But let's use this idea of the density of states. So we know that the density of states, dE, is the number of states that are available at a certain energy, and all of them are filled, whatsoever are available. So if I take the number, so this is a number per unit energy. If I integrate this over energy, and I integrate from 0 energy, and I'm ignoring ground 0 point energy because it's too small as compared to the Fermi energy, and I put the upper limit as EF, then this should give me this, correct? So let's call this is some constant C, E 1/2 dE from 0 to EF. This will give me C EF 3/2 2/3 N. All right. So this EF is related to N. So EF will be proportional to N by 2/3. Higher the number of electrons, higher will be the Fermi energy at 0 kelvins. So denser metals, in principle, if this free particle model is correct, will have a higher Fermi energy. Higher valence metals will have a higher Fermi energy. And you can look up a table in any standard textbook. This tells you the charge density and tabulates the values of the Fermi energies. Okay. Have you ever encountered the idea of a Fermi energy or a Fermi level in any other course or your A levels or any other idea? Where did you encounter Fermi energies? Huh? Statistical mechanics. There you must have studied chemical potential as well. Chemical potential भी तो पढ़ा होगा ना? Chemical. उसके बगैर नहीं हो सकता स्टैटिस्टिक्स. ग्रैंड कैनोनिकल एंसेंबल. केमिकल पोटेंशियल भी पढ़ा होगा. सॉरी, स्टार्स की फॉर्मेशन में भी. स्पीक अप. At 0 kelvins. No, at 0 kelvins all the levels up till the Fermi energy are filled. इसके ऊपर भी levels, so there are huge number of levels available beyond this, and the electron can go there if it wishes so, but it doesn't need to. In equilibrium, in the ground state for the system, only levels up till the Fermi sphere will be filled, but other levels are available. So if you increase the temperature or then apply an electric field or apply stress or apply a potential gradient, electrons can be excited, promoted to higher levels. Levels तो available है. एक खाली एटम के लिए आमतौर पर फर्मी एनर्जी का कॉन्सेप्ट इस्तेमाल नहीं होता. एक वैलेंस इलेक्ट्रॉन खाली एटम पड़ा हुआ है, इट्स नॉट इंटरेक्टिंग विद एनी अदर, दैट्स एटॉमिक फिजिक्स, दैट्स नॉट कंडेंस्ड मैटर फिजिक्स. सो यू डोंट यूज द टर्म फर्मी एनर्जी फॉर अ सिंगल एटम. ठीक है. नहीं, सो these electrons are unbound. These electrons do not belong to any atom. They do not, so they have all, the atoms are already ionized. So these electrons are unbound, free electrons. But when you talk about atoms, those electrons are bound to the atom. Okay. So one, yes please.
Sir, आपने बोला 0 point energy को हम zero से करें. वो 0 point energy आ कहाँ से रही है?
0 point energy तो वैक्यूम फ्लक्चुएशन से आ रही है. h bar omega by 2 जो भी है. ये this electron is also a field. Just like we have a phononic field, the electrons are also like a field. So they are quantized. It's a quantum field. So the minimum energy of a quantum field is the 0 point energy. Even though we have not quantized, we have not gone through the rigorous process of second quantization because it's not needed here. But really this electron also is a field. So this approach that we're using is semi-classical. It's using the Schrödinger equation, but it's not second quantization. These electrons are still not being treated as particles here. Now one thing before we move on is, so let's relax this condition for 0 kelvins a little bit. We know that for bosons and for phonons, for example, we came up with this factor F, which was 1 over E h bar omega over kBt minus 1, right? So this is the average number of, we call this in our previous discussion, the average number of phonons that exist at a temperature T with frequency omega. Correct? So this factor is called the Bose-Einstein distribution factor, and this is valid for bosons. So if a state is available, that state is really a mode of frequency omega. State is defined just by a mode omega, frequency of omega. For phonons it could also talk about the branch, which branch you're talking about, but it's primarily defined by omega. and that omega comes from a k. So this factor tells you that if a mode exists, what's the probability that the electron will be, that the boson will be in that mode. It's a probability of occupancy of a mode. And this is equal to the average number of particles, average number of bosons that exist at this frequency omega. Right? This is how we treated when we derive the total energy inside a phononic field. So this factor here is valid for bosons, the Bose-Einstein distribution factor. Okay? For fermions, this factor changes. For fermions, this factor, let's put another symbol here, Be, for Bose-Einstein. Omega at some temperature T. For fermions, which electrons, this factor is now has to be replaced by a Fermi-Dirac distribution function. Correct? Because they obey the Pauli exclusion principle and the distribution factor changes. So now we have a new factor F, let's call this Fermi-Dirac distribution function. This is different from this function and is given by E, energy. So this is really an energy, h bar omega is the energy of the phonon or the boson. E minus the chemical potential, mu. Okay? You must have studied mu inside your statistical mechanics course. So how far is that energy? So instead of omega, I'm using E. That's conventional for fermion. So how far am I from the chemical potential? Divided by kBt, same factor as this, and this negative sign now becomes a positive sign. So this factor is called represents the Fermi-Dirac statistics. For this Bose-Einstein distribution factor, this is also an energy, but for phonons and for photons, the chemical potential is 0, right? So this factor mu does not appear over here. So what we have now is a Fermi-Dirac distribution function, and if I were to plot this Fermi-Dirac distribution function at 0 Kelvin, so let's plot this. Let's plot what this function looks like. It's a probability distribution function, which tells us if I have an energy E state available, what's the probability that a particle can be found in that state. Got it? So if I plot this function, this is my E. Mu must have dimensions of energy again. What will the plot look like at t equals 0? So this is what it looks like. For E greater than mu, this term is positive. So positive over a very small number. And this small number is positive over a small number. So this becomes very large in the positive sense, but you get a 0 here. This is 0 here. In the case that mu is larger than E or E is smaller than mu, this is e raised power 1 over e raised power minus some beta x plus 1. Okay? So this is negative. Now beta is really, really large right? Because beta is 1 over kBt. If kBt is small, beta is large. Okay? When beta is large, this becomes really small. So this becomes 1. So you're left with 1. Okay? And here you have a discontinuity. So this is what the Fermi-Dirac distribution looks like at 0 kelvins.
Sir, यहाँ पे why is the chemical potential appearing? हम तो free electron से शुरू कर रहे हैं, तो like इस case में तो chemical potential affect नहीं करना चाहिए हमारी distribution.
तो chemical potential temperature की वजह से तो change होगा, ये हम prove करेंगे. ये temperature dependent, is weakly dependent on the temperature. ठीक है? So this is the scenario at 0 kelvins. At 0 kelvins, what this distribution function is telling us is that up till energies, up till mu, there is maximum probability. It's equal probability, that likelihood is 1 that state will be populated. So at 0 kelvins, the chemical potential is the Fermi energy. That's how we can define the Fermi energy. The Fermi energy is the chemical potential at 0 kelvins. Because all the states up till this energy are populated. Correct? So this is one way of defining the Fermi energy. The Fermi energy is the chemical potential for electrons at 0 kelvins. Correct? Now, one thing, if I now relax this condition for the temperature being 0 Kelvin, the temperature goes slightly beyond 0 kelvins, this Fermi-Dirac distribution function is going to change slightly, only slightly. And how is it going to change? Temperature is now higher. It's greater than 0 kelvins now. Abhi keh rahe hain mu is constant. Mu is still is not changing. How is F changing? Now this is no longer 0 here. It's some number. Could be a small number. T is small number. 1 Kelvin, 1 millikelvin, 1 microkelvin, 2 Kelvin, 5 Kelvin.
F is a mu पर I believe half बन जाएगा.
क्या बन जाएगा? Half हो जाएगा. So this line will slightly, this sharp edge will slightly smoothen out. So at even higher temperatures, this line is going to smooth out a little bit more. And I've actually exaggerated this smoothing out quite a bit, because the presence of this exponential factor doesn't let lots and lots of deviation from this sharp edge. So what this means is that at higher temperature, beyond 0 Kelvin, some of the electrons that were found in this part of the lobe kind of go beyond the Fermi energy. That's what it really means. So some of the electrons can be excited to higher energy levels beyond the Fermi energy when the temperature goes up. But this spreading out, this fanning out is shown highly exaggerated here. It's a very small spreading out. Okay. So now what we would like to do is we would like to find out, say, the total energy of the system, the total number of electrons in the system at any temperature beyond 0 Kelvin. So here in this example, everything was at 0 Kelvin, so the upper energy level was EF. And there was a hidden Fermi-Dirac distribution function F here, which had a value of 1. Anyway, at 0 Kelvin, at energies below EF. So this factor, there was a factor F here which was equal to 1. But at temperatures above 0 Kelvin, we have to explicitly put in an F. Okay, and this upper limit goes to infinity. So if at temperatures above 0 Kelvin, I would like to find out the total number of electrons. I integrate over energy, the density of states, and F E. Now I'm not going to write the FD over and over again. I'm assuming it's a Fermi-Dirac distribution function. By the way, if you look at the these distribution functions for large temperatures, these distributions become the Maxwell-Boltzmann distribution functions. Alright, so this is how you find out the total number of particles in a system at any energy, at any temperature, even beyond 0 kelvins. So now this F has to be explicitly put in, F has to be put in. And by the way, if you increase the temperature, the number of electrons in the system is not going to go up or down, it's going to remain the same. Okay, so this really remains equal to 0 to EF dE dE. Oh, sorry, dE. So these three quantities are equal. This is also equal to capital N, and this is also equal to capital N. So this expression is at 0 Kelvin, this expression is at 0 Kelvin, but they should yield the same integral, right? So this we do know is CF EF raised by 3 by 2 into 2 by 3. This we do know, right? The formula that we've written over there. Now, how do we find out expressions of this kind? For example, I'm not going to solve this integral right now. We're going to do this in the next class. We're going to use a technique due to Sommerfeld, which is called the Sommerfeld expansion technique. So, what will be the total energy associated with the electrons, the free electrons inside the solid? We found out the total energy for the phonons. हमने technique से बिल्कुल exactly the same technique. The number of bosons, which was the Bose-Einstein distribution function, multiplied with the density of states into energy integrated. That's how we found out the total energy for the phonons. Now, can anyone come to the blackboard and just write down the integral, what the integral is going to look like? The total energy associated with this gas of electrons inside the solid. From that, we can find out the heat capacity, for example. सिर्फ इंटीग्रल लिखना है और कुछ नहीं करना, सॉल्व नहीं करना. अच्छा, आसान है, इसी से मिलती, इसमें एक टर्म ऐड हो जाएगी बस. डर लिखो. एनर्जी ई है बस.
हाँ, लेकिन इसके अंदर क्या आ जाएगा ना मेरे पास.
नहीं, ई लिख दो ना
बस ई.
हाँ, right. So this is the total energy inside the system. All right. So how do we solve integrals of this kind? So at 0 Kelvin, this becomes equal to 1 and this becomes EF. So everything is easy at 0 kelvins. So you can find the total energy. So for example, at 0 kelvins, say at 0 kelvins, the energy of the electrons, is it going to be EF? No. It's going to be different from EF, but it's going to depend upon EF. So this is 0 up till EF, dE, E, C 1 by 2, this gives me C 3 by 2. Right? So half E raised to power 1 by 2 comes from here, 1 comes from here, so this comes C, EF 5 by 2 2 by 5. Correct? So the total energy for electrons is EF raised to power 2.5. And what's the average energy for an electron inside the solid? So the average energy, U average, this is the total energy. U average will be this total energy divided by the number of atoms that exist, number of electrons, sorry, that exist. So we have 2 over 5 C E raised to power EF raised to power 5 by 2. And what's the number of electrons in terms of EF? We've written this somewhere. This one. Three by 2. So this will be 1 by 3. ऐसे ही है ना? So if I were to draw an energy level diagram for the electrons,
So, 3 by 5.
sorry. So if I have a container, so it's a 3-dimensional infinite well, remember this? In this container, this is my zero energy, this is my Fermi energy, EF. When we draw energy level band diagrams, energy level diagrams for semiconductors or for electronic structures, this is how we generally do it. So all the levels up till EF are filled. And there are millions and millions of levels, even though I've drawn this as a continuum, these are finely spaced levels. Okay? Finely spaced levels, not equally spaced levels, because we do not have a harmonic oscillator here. These are finely spaced levels, unequally distributed, because the density of states is a square root function of E. At 0 kelvins, all the energy levels up till EF are filled. And the average energy for this system is somewhere over here. 3/5 of EF. Which means these are not, there's sparse density here and higher density here because of the 1 over E raised by 1 by 2 factor. Okay, so the average energy for the electrons is here, and this is the maximum energy. If I have two solids and everything is at 0 kelvins, two solids, and they come close together, the Fermi energy is higher here and it's lower here. Then electrons, if they make contact as they do in a p-n junction, the electrons can go from positive charges, the electrons can go from this level to this level because empty vacant states are available here. So that's what happens in a p-n junction. When there is gradient in the Fermi energies, the difference in the Fermi energies, electron transfer can take place. So this is how we describe electronic structures, this is how we describe semiconductors, how different kinds of diodes work, and so on. So this is a whole field in itself. And this is the beginning of semiconductor physics and electronics. So the next lecture, what we're going to do is we're going to find out how does the chemical potential depend upon temperature, how do we get heat capacities for electrons in 3D, 2D, 1D, and we'll also probably see how do we get magnetization, because then we'll put some spins physics into the picture. After one more lecture, we'll move on to band structure and relax this requirement of electrons being independent. Then they will see the periodic potential and we'll start getting bands inside the solid. Thank you very much. So I'm preparing homework